Welcome to Cloud Native Compass, a podcast to help you navigate the vast landscape of the cloud native ecosystem.
We're your hosts. I'm David Flanagan, a technology magpie that can't stop playing with new, shiny things.
I'm Laura Santamaria, a forever learner who is constantly breaking production.
Do you want a single database to store high-precision, multi-dimensional time series data that supports infinite cardinality? Well, we're not there yet, but Paul Dix does share his vision and roadmap for InfluxDB 3.
Do you want to hear David not have to talk about Rust to get a guest to actually talk about Rust? Now's your chance. In all seriousness, we not only get to talk about a move from Go to Rust, but also about observability and how it's changed over time, as well as a little bit about open source licensing changes.
So let's Rust. Go. No, but really, let's all Rust. All right. Thank you for joining us, Paul. And for anyone who's not aware, can you please tell us a little bit more about you and what you're up to?
Yeah, so I'm Paul Dix. I'm the co-founder and current CTO of InfluxDB. We are the company that make InfluxDB, which is an open source time series database. It's useful in use cases like tracking system metrics and application performance metrics, sensor data, that kind of stuff. My background is as a programmer. I started the company in 2012, and we went through Y Combinator actually under a different idea, and then we pivoted to this idea in the fall of 2013.
Awesome.
Yes.
Thank you.
There's more. I can go on like at length, but I'm trying to be concise. Yeah.
All right. Well, let's talk about your work on InfluxDB. So over the last, I'm not sure how many years, you started work on a rewrite of Influx, moving towards using Rust on a project called IOx, which I believe this year you have now pushed out into production as part of your InfluxDB cloud offering. So I really wanted to kind of drill into that and just understand more about, one, why a rewrite, changing programming language, re-architecting the system, using Apache Arrow, a huge task for a company to take on, and I'd love to know more.
Yeah, so I'll just start with the obvious, which is a rewrite is basically like the worst possible thing you can do. Like, unless you're just like a sadist or a glutton for pain, you should avoid a rewrite at all costs. Okay, that's out of the way. So InfluxDB, the original version is written in Go, and the core architecture of the database is built around what I would call like a clever hack, right? So it's kind of like two databases in one thing. One is basically a time series database that organizes data on disk as individual time series, which are value timestamp pairs in time ascending order, right? So as all the data comes in, it tries to organize that data on disk in that format, which is basically like a very like indexed format. The other piece of this is an inverted index that maps metadata to individual time series. So the metadata is like a measurement name, a tag key value pair, a field name. So just like, usually people are familiar with inverted indexes from document search, where you have a document, you have an inverted index of the words that appear in the document. And then when you search, you find the words and you find the documents that have those words, right? In this case, we say, tag key value pair, like host equals, server A, or region equals US West. And then you find the time series that match that piece of metadata, right? So what that means is as you're ingesting all the data, there's a lot of indexing work that happens, right? So it chews through like a lot of CPUs and stuff like that, and it reorganizes the data. Now, when a query comes in, if the query is for one individual series, generally those queries are very, very fast, right? This is a system that's optimized for that kind of query workload and for that kind of like needle in a haystack query, specifically on, the individual series and the time range that you're looking for. But again, like the problem becomes as your index, the set of metadata that you're tracking grows, commonly referred to as like the cardinality problem, right? The number of unique tag values that occur, just the number of individual series that occur, you spend more and more time indexing the data, and it just becomes more and more expensive to ingest it, right? You spend more CPUs, you spend more disk space storing the index and like all this other stuff. It becomes really painful, particularly as you try to add like more and more granularity and visibility, like more precision into the measurements that you're taking, right? Like, again, more kind of metadata that you're capturing around those things. And then the other side of this is when you want to do a query, if you have a query that's going to touch, tens of thousands, hundreds of thousands, or even millions of individual time series, right? You want to do an aggregation across, all these time series in a region or whatever and compute something. Those queries become prohibitively expensive. And oftentimes you can't even do them because the engine will just like fall over, right? The way to do it and to map it onto that index structure is just way, way too expensive. So basically that's the version of the database written in Go, version 1, version 2, same storage engine. We wrote a storage engine from scratch that kind of has this architecture. And we created the initial version of that storage engine in, I lost my screen for a second. Hopefully we're there. Where we created the initial version of that storage engine I prototyped it in the fall of 2015, and then we had the first release in early 2016 that had that. And we've iterated on it and added to it over time. And essentially what we found over, the next whatever number of years, 4 years, is that people wanted to have higher cardinality data. They wanted to feed in data where they actually didn't have to worry about the cardinality or the ephemerality of the values that they were feeding in. And they wanted to do more analytical queries across it, right? And all of this stuff was built around our query language, InfluxQL, which is a query language that looks kind of like SQL. So it's kind of familiar and friendly, but it's for people who really know SQL, it can be frustrating in unique ways because it doesn't actually work exactly like SQL. But for some things, it's super easy to create like a time series query or whatever. So again, there were multiple problems we were trying to solve for. How do we solve this cardinality problem? How do we give people a query engine that can be useful for analytical style queries on larger chunks of data? And then this other piece, which was we needed to figure out how to store a massive amount of data at a much more cost-effective way, right? InfluxDB 1 and 2 have just a base level of assumption that you have a locally attached SSD or, whatever, like an EBS volume, a high performance network volume with provisioned IOPS and whatever. And all of your data is stored on that. And it's super expensive. And for a lot of our use cases, right, people could have a year's worth of data, but 99% of their queries hit basically the trailing few hours or few days worth of data, right? But they want this stuff available and accessible, but they don't need it available, accessible, at the same response times. And they definitely don't need it stored on expensive NVMe drives or whatever, right? So we needed to figure out a way to decouple the compute of ingestion and query from the actual storage of the data, right? And obviously, all this stuff is building up over the course of 2017, 2018 is when I'm noticing this. 2019, it's just becoming more apparent. And the thing is, also during this time, there are interesting things happening out there in the infrastructure world, right? The rise of Kubernetes, for example, wasn't there when we first created InfluxDB. So this idea of containerized applications and this ephemeral application stack or ephemeral compute stack that you layer on. And then the other thing, the rise of object storage as basically a common storage layer. Those things happened over the course of, that decade of, the 2010s. And I think one company that really took advantage of that, at least the rise of object storage and decoupled compute from storage, was Snowflake, right? They're the first company I think that really commercialized this idea of we can create this big data system that stores data super cheaply and just layers on compute on demand to execute queries on it. Now, Snowflake is obviously designed for a completely different use case than InfluxDB, right? Snowflake is a data warehouse. data at scale, whatever. InfluxDB is about operational data and real time, right? You need to be able to query it within, milliseconds of it writing it into the database. And you need those queries to return generally sub-second so that you can build monitoring alerting systems on it. You can build real-time dashboarding. So in 2019, I started actually in the fall of 2018 is when I started picking up Rust. And I thought I first commit on InfluxDB was in 2013, but the basis technology that we built for it was actually we had done and started in the fall of 2012. And Rust was not in a place where I would use it then. I used Go because I thought we will be able to move faster creating the database. We use Go as the language. But in 2018, I started picking up Rust and thinking, okay, this is actually interesting. And then in the fall of 2019 is when the async await stuff landed in Rust. Mm-hmm. And when that landed, I thought, okay, this is probably going to be a serious language for building server-side software where you have to handle network requests and all this other kind of stuff, right? That was, I think, for me, that was the final piece that I was looking for. That Rust had actually arrived at a point where you could use it to build a complicated piece of server software and you wouldn't have to build everything yourself, right? There are certainly successful projects in Rust that started before that, right? Like Linkerd did that, but that point, I was like, okay, that's interesting. So coming into the beginning of 2020, which is when I kicked off this project, I just said, okay, we need a different database architecture. This combination of this inverted index plus this time series storage and the way the entire database engine works is not going to work for what we want to build, for the requirements we want to meet, right? We're using memory mapped files, which is again, you're not going to get that in object storage, and it's not great to use in containers and all this other stuff. So I was like, okay, if we're going to re-architect the entire database, that's basically a rewrite of the database. We could do it in Go, and there's a bunch of stuff that exists in Go that we would reuse that obviously wouldn't be rewritten. The language parser and all this other stuff. But basically, I was looking at the project and I thought, this is a rewrite. If we actually try to make these big changes. And again, in late 2019, early 2020, one of the other things I noticed out there in the world was Apache Arrow. I'd known about the project for a little while. Apache Arrow is an in-memory columnar format specification. And I was looking at that, and I was looking at Apache Parquet, which is, file format for this kinds of structured analytical data. And I thought, well, I think there's really something interesting here. So again, I wrote some blog post in early 2020 where I said, I thought that the different pieces of the Apache Arrow project would become a way for companies that are building data warehousing systems and big data systems and streaming data systems, basically all these analytical systems that are working on observational data of any kind, right? Whether it's server monitoring data or sensor data or whatever, those standards would become a way for people to collaborate and build, common infrastructure, but also proprietary solutions. And those will be the touch points in terms of how you exchange data between these systems. So that was kind of the thesis in early 2020. Rust as a language is going to be better because one, the multi-threading support in Rust, I think is just the way it handles it is way, way better, right? Because it's kind of enforced by the compiler. We wanted strict control over how memory is managed and that kind of stuff, which obviously basically we didn't want a garbage collected language. Performance was going to be a critical thing. Go is super fast. Don't get me wrong. I love it as a language. It's way easier to learn and work with than Rust, I think, in my personal opinion. But I just thought for this kind of software, for a database system that has to perform at scale with high performance, Rust just seems like the logical choice. And if it wasn't Rust, it would be C++. But I think in this day and age, it's just a better choice to use Rust.
Yeah.
And then over the course of the next, 3.5 years, initially we it was basically like me and one other guy within Influx for a couple of months. And then we hired somebody else, Andrew, who's still with us. And basically the three of us kind of treated it as a research project almost for the first like 6 months. It wasn't like, within the company, there's no way I was going to get like people to buy off on, oh, Paul wants to rewrite the database. Like, yeah, let's put a bunch of effort into that. No, it was basically like, I'm going to do this as a research project because I think it's interesting and I'm going to see where it leads. And then by November of 2020, we'd had enough of the pieces figured out, right? We're going to use Apache Arrow. We're going to use Parquet as the persistence format. Object storage is where all the data is going to live. Apache Arrow Flight was going to be the RPC mechanism that has since evolved into Flight SQL, which is a new standard they have for essentially doing RPC and SQL queries in these kind of data systems. And a project called Apache Data Fusion. Right now, it's a sub-project of Apache Arrow. Its Data Fusion is a SQL parser, planner, optimizer, and execution engine written in Rust. And we're like, at that point in the summer of 2020, when we decided to build around these things, Data Fusion wasn't even close to as far along as it is now. And we knew that we'd be like investing significant effort. Like we actually looked at using other SQL engines as the core of the database. We looked at some C++ engines just to think like, maybe we didn't want to write our own, but we needed something that was like optimized for our use case for time series. And we saw that regardless of what we picked up, we would end up having to do a lot of work, and we'd almost have to take partial ownership of the project. And we thought this umbrella of projects under Apache, under the Apache Foundation, under Arrow, were, they were early, but they were promising. And if we really put our effort behind it, it would cause more people to also start programming against it and whatever. So in November of 2020, I announced like, hey, working on a new core of the database. It's called IOx because nobody was comfortable with me calling it InfluxDB 3.0. Because again, they're like, you're not going to rewrite the database. So there's no way we're doing this. I was like, well, let's just see how it goes. But yeah, at that point I announced it, and still it was like 3 of us working on it. It was still very, very early stage, but that allowed us it got, a number of people out there in the world interested in the project, and we hired some great people that joined us, so that by March of 2021, we had a team of, I think, 9 people. And we spent years writing a database, which we launched into production earlier this year.
So how long did it take before you were allowed to call it 3.0? Before people stopped telling you, no, you can't rewrite this database?
We announced publicly that it was InfluxDB 3.0 on April 26th of this year.
So inside the company, it took you like 2 or 3 years to get everybody on board with the idea of, no, really, we did, and we're about to finish it.
I would say by probably, it's basically by, I'd say, 2021, like summer, fall of 2021, people within the company are like, okay, we need this like new core of database engine, because like at that stage, it was obvious what the limitations of the previous engine were, right? In the beginning, people were like, Paul, what are you talking about? Like, there were some people who got it intrinsically, and other people were like, we don't need to do this right now. And then by, again, like I'd say, like the fall of 2021, everybody in the company was like, okay, we definitely need this new database engine. When's it going to be ready? And I'm like, guys, we're not baking a quiche here. Like, it's going to take some time.
Yeah.
So yeah, by I'd say like the spring of 2022, it was like, okay, this is obviously what we need to be doing. And then definitely by the fall of 2022, it was like, okay, we're getting everybody focused on this new database engine, and we're going to call it 3.0. Then it just became a question of when when we were going to be more public about the fact that it was 3.0. But in my mind, it was always InfluxDB 3.0. Even though it is a total rewrite and the database architecture is drastically different than the underlying database architecture of 1 and 2.
All right. Nice. I love that we just ask a question and then set you loose, and then you just go for it.
Sorry. Yeah.
Go for it. No, don't be sorry. That's the good part. It's fine.
Well, I don't know if there should be more back and forth.
No. That was absolutely perfect. And, you kind of answered my second question, which is good as well, because we're thinking through the problem space well here. And I think there's a lot of context about what happened in the industry, what happened with the early versions of Influx, why this rewrite was required, why Rust, why Arrow, all these things now make a lot more sense, right? But, let's reemphasize one of those things you talked about with the 2010s. It's like this was the decade where containers and cloud took off, right? People were using ephemeral compute, spinning up VMs on AWS, GCP, Azure, launching dozens to hundreds to thousands of containers orchestrated with Kubernetes. And all of these have their own signals. They have their own logs, they have their own metrics, they have their own traces. Traces are now important because at the same time of this wild cloud container orchestration evolution, people decided to start doing microservices because the technology enabled all these new architectures too. So I spend a lot of my time, I'm just going to set context and not ask questions and then just let you infer the questions. But still, I spend a lot of my time working with companies that are trying to build out platforms. They want to make it easier for their developers to deploy to production. And I think one of the challenges I've seen is that people really struggle with, I need a database for logs. I need a database for tracing. I need a database for my metrics. I then need to be able to aggregate and query and all this stuff. And they make it really complicated for what is in essence all the same data structure. I don't think there's that much difference from a metric, a trace, and a log. It's all a collection of events. The difference between a trace and a metric is that it's an aggregation of some raw level event. And the challenge has always been the cost of storing it at this super high dimensionality, with super high dimensions, versus the easiness of querying it, which is why we probably do metrics and terrible versions of histograms and all this other stuff that we now accept as the norm, right?
Yeah.
And I'm going to quote something on your website that you might hate me for, right? But when we talk about IOx and DB3, you specifically say infinite cardinality. Yeah. So the question is, does IOx give us, or can it, or InfluxDB3, give us a single store for all of these signals, all of this observability and monitoring data? And can you give us a bit more insight into what that infinite cardinality actually means in a practical term?
Yeah, so to store the data, yes, 3.0 can store all of that kind of data, right? Because of the fact that cardinality doesn't matter. The problem becomes what happens when you try to query that data, pulling it out, right? And that's basically like the patterns for how you query the data and what people expect are why you end up with, I think why you end up with 3 different systems for storing each of those kinds of data, right? Traces, metrics, and logs. In my mind, they're all just like different views of the same thing. Ultimately, like if you wanted to, you could just have traces and skip the logs and metrics, right? You could derive everything else from raw traces, because traces, again, like you could have just a blob string field in the trace that has log info, right? So, but the problems are like what happens at scale, right? And when you start generating a ton of this data, do you end up having to sample it? And then how do you actually access the data? What are the access patterns, right? So for right now, the metric access patterns are like, I have this metric and I want to look at it. And the idea behind metrics is metrics are a summary view of some underlying distribution or some underlying thing that you're tracking. Generally, metrics are not the raw high precision view, right? For example, if you want the average response time in 1 minute intervals to an API call, right? A specific like API endpoint, right? Now, the raw view is individual requests, right? And you log every bit of detail you would want on that request, right? What host received the request, what user submitted it, what token they were using, what endpoint, the actual data included in the request, the response time, the response itself, right? You can get down to just an insane level of precision. But the problem is, to do that at scale is completely unreasonable, right? It generates like more data than you ever even stored and all this other stuff. So you end up creating these systems to summarize things. And the problem that people frequently run into is like, well, if you didn't think ahead of time of what you needed to summarize, when you go to look at the summaries, your metrics, the answer you need isn't there. And the request's already happened, right? So logs are a way to capture more detail and then kind of like try to figure it out after the fact, right? So the idea with logs is it's something where, you know, you're doing an ad hoc investigation where you're not continuously like looking for some signal that triggers like a problem in the system. But so ultimately, like storing all that data, you can use the same format. Parquet as a storage format, for example, can store all that kind of data. But querying it effectively and efficiently is difficult. And that usually requires either secondary indexing structures or other ways to organize the data so that you can actually query it effectively. Now, aspirationally, 3.0 wants to be the home for all that kind of data, basically for any kind of observational data you can think of, right? And like for us, it's not just like, you know, these server infrastructure monitoring use cases, but also more and more sensor data use cases. And again, with sensors, you find the same kind of thing, right? People can deploy more sensors in their environment for the machines they're tracking or the environments they're tracking, but that they can also increase the precision of the measurements, right? They can increase the sampling interval. They can increase the precision in terms of what gets tracked with each measurement that gets created, right? And that's all the metadata that you could potentially track about something. With sensors, you could be, again, like all the stuff around the customers or the users. It could be around the location, the lat long, like all that other kind of stuff. So getting there, like we're there in terms of being able to store it. We're not there in terms of being able to query it. We organize data into large chunks, and then the query engine just kind of brute forces those chunks. So I think that is going to take some time to get to the stage where we can actually do all those things. I think there's some other stuff around like with logs and tracing use cases where the schemas are very, very dynamic and they're not always consistent, right? If you try to like pull out structured fields from these things, a lot of times people won't have the same field types for something that's named the same thing because they're in different services or whatever. So those are all just like kind of like weird.
They're fun.
Yeah. Infrastructure, like horrible, like problems that you just end up having to deal with. So whereas like right now, I would say with 3.0, it's better for like structured events, right? Where you have events that you're tracking and you want to get high precision data, right? Where you can slice and dice it any way you choose, right? So systems where you can think of like use cases where you think that'd be good is like if you're doing usage tracking and an API, audit logging, any type of individual events. Metrics is also a use case, obviously, that InfluxDB is used for, and this engine is useful for as well. But logs and traces are a bit trickier because of again, like kind of how flexible the schemas are as people deploy them in different systems. And the thing with tracing that's weird is I think most of the tracing front ends look like you're looking at a metric view or a log view, and it's like, oh, go look at the trace. So basically what you're doing is you're jumping off to look for a trace by a trace ID, right? Which is essentially that implies what you want is an index which maps an ID to an individual trace. And of course, a time series database isn't really designed to do that, or like the way our database is structured is not really designed to do that. Now, there are ideas we have for being able to layer that in without having to create super expensive secondary indexing structures, but all of that stuff is going to take time. So I think with tracing, would make it easier is when you have a trace ID, you basically always have a time range as well. So for a system that stores traces at scale, it would be easier to say like, oh, give me this trace ID, but this is like the time envelope that it appears in. At least that's what I'm imagining make it easier. But yeah, I don't know. Yeah, metrics, logs, and traces is basically like the gold standard for how you do observability right now. But I don't think that's the end state. I think it's not ideal. Like the usability isn't ideal. It can be painful. Tracing is tracing is expensive from a development perspective in terms of putting it into your code, but it's also expensive in terms of like an infrastructure and like being able to collect all this data. And then you get into like figuring out, okay, do we need to do sampling because there's too much? And I don't know. It's all still too difficult to use, which tells me there's a lot of room for innovation. But the thing is, there are a lot of really smart people trying to fix these problems. It's just really hard because of the volume of data keeps increasing and the demands of the user base also keep increasing. Right.
Yeah. I used to work at a logging company, and back around the same time when you were discussing how do we move this off to other things. And I remember that being part of the discussion, that we were handling petabytes of data, and how do you handle just that much? But I'd find it interesting, do you end up with a lot of legacy systems as well? Because that was always the issue with the logging, is that to go back and change it from the string that who knows what the developer decided to put in there, if they decided to put anything in there. And then there's all these different levels of logs, and they're all strings that you have to figure out how to parse. Then eventually people moved to structured logging, but that wasn't a thing. So that's a whole nother can of worms to open, I imagine.
Yeah, I mean, you have to either like parse the legacy logs into some sort of structure, right? I mean, and again, like the structure is really about query performance, right? Because you could create the structure on the fly, right? You could just store all the logs and whatever, and basically like at query time, parse each log line in the structure. And again, like you could do this on the fly to be like, oh, well, that query didn't work, but I got this error back. So I'll change the way I'm structured. I'm trying to parse that particular line or whatever. But the problem is that those queries are super expensive to run, right? They cost a lot of CPU, right. They cost a lot of network bandwidth. So really like the thing about structured logs and even metrics is about essentially introducing structure and summarizations that make the queries efficient enough to run for whatever the use case is. And I think that's also one of the things to keep in mind is like, is this a case where you're building for a system that does automation where it needs like the query to return in, tens of milliseconds, hundreds of milliseconds? Is it something where it's like, and that, the automated systems generally like those queries run all the time, right? Many, many, many times, right? Or is it an ad hoc query from a user who's doing some investigation, in which case they're more than willing to wait tens of seconds for a return. And those queries are few and far between, right? You're not doing that many of them. And I think the ad hoc thing is probably easier to solve with that pattern of let's take these blobs of data, put them into object storage, and spin up compute on the fly to handle those. Mm-hmm. It's the real-time systems where you have to really think about layering in structure and optimization so that you can answer the queries fast enough.
All right. So you mentioned at the start how you had this InfluxQL in version 1, this SQL SQL-like language that frustrated people because it wasn't real SQL that they were familiar with working with other databases. With Data Fusion, do people get access to more traditional SQL? That's part one of the question. Part two is with InfluxDB 2, there was a lot of investment into the Flux language, with the messaging around how Flux was purpose-built for time series and SQL wasn't. I'm curious if that has changed, and do we feel now that SQL is the right language for time series, or is there still a future for Flux with InfluxDB 3?
Yeah, so first I'll mention about InfluxQL. So some people found it frustrating because it was unlike SQL, but a surprising number of people have told us they actually prefer InfluxQL to SQL for writing some basic time series queries, right? Because it's just like super easy to write a thing where you're, getting a summarization by these, different things. Whereas like in a SQL engine, you might have to deal with windowing functions and partitioning and like all this other stuff. So I think InfluxQL has a place that will continue to serve, just because we've gotten that feedback that a number of people actually prefer it to SQL. So with Data Fusion, we have a fully featured SQL engine that supports all of these things: joins, window functions, partitioning, like all this complex SQL stuff. We've been adding in more and more functions to make time series stuff, to make it more capable of doing like time series specific style queries. And we'll continue to do that. We're certainly not done with that. So the thing with 3.0 is, again, it's built around this Data Fusion query engine, which is a SQL engine. Now, all that's written in Rust. Obviously, 2.0 is written in Go, and Flux as a language we developed for 2.0, and we developed it. So there were a couple of things. One, for the users of InfluxDB 1, they frequently had requests that they just wanted to express more arbitrary and complex logic in their queries than could be expressed in InfluxQL or indeed in SQL. So we were just like, we need a scripting language paired with a query language so that people could do more complex things. And it became like, oh, you can use this also to connect to third-party systems, to join with your time series data on the fly, or to send data out to third-party systems, right? Be it another database or a third-party API or whatever, right? So that was part of it. Another part of it was, I had a thesis back in I originally in the fall of 2014, I was talking about changing the language from InfluxQL to potentially something that looked more like a functional language, which is what Flux is. And I decided at that time to stay with InfluxQL. But I had a theory that I think for the time series use case, a functional language would be better, would be more like expressive and more powerful for working with time series data. And Flux was our attempt at that, right? And I think, so we built obviously the Flux language, the scripting language, the query engine, the planner, the optimizer, everything from the ground up, which is a very large, that's basically two very large separate projects. And all of that is written in Go. Now, coming to 3.0, we thought, okay, we need a way to bridge Flux, and we also want to see if we can bring over InfluxQL. And with InfluxQL, we had the idea, well, it looks like SQL, so what we can probably do is write a parser in Rust to parse the language, which isn't too hard to create, that will then translate an InfluxQL query into a Data Fusion query plan, right? So we had one person start on that in the summer of last year. And basically now, this year we have that actually works, and it works really, really well, right? And it was basically just one person who did a lot of that effort. Last fall, we added on additional people onto the team to build the last bit, which is API bridge, which is, to represent all of that with the InfluxDB 1 query API. So we're really happy we were able to bring that over, and it gets all the benefits of that Data Fusion query engine, right? So when there are performance optimizations or other things like that, they just come, when we pull that in, InfluxQL gets all of that for free. Now with Flux, what we tried to do was the surface area of it is way, way too large to try and create it again in Rust. Although I would love to do that. It's just way too big of a project to do, and we don't have the time or resources to do it. So what we did was, in our Cloud 2 platform, we had Flux processes that communicated with the old TSM storage engine via this gRPC API. So what we did was in 3.0, we created that gRPC API, and we connected Flux up to it. And what we found through like some production mirroring and actually letting customers test it was, one, that gRPC API was like it had some edge cases that were poorly specified. So there were weird bugs that would pop up that we just unforeseen bugs, like that would surface in the Flux query, things that worked on the previous one that don't work on this. But more importantly, the performance of that bridge was not good, right? Basically there were queries that would work in the old Flux to TSM version that worked in a decent amount of time, and queries on the Flux to 3.0 bridge that just like timed out. And again, like one of the things we were trying to do with 3.0, one of the reasons we adopted this new query engine is because we wanted queries to be super, super fast, right? Query performance was a super important thing. And a lot of Flux queries, like we saw there were queries that just wouldn't work in that engine. So when we created this bridge, because of the way that API works, it's built around how data is organized in that TSM storage engine. And the 3.0 engine does not have the same organization. So in order to present the data in that organization, the 3.0 engine has to do a lot of like post hoc sorting and filtering. And that sorting is basically you chew up CPU time doing that. And basically it wasn't performant. So like right now we have a theory that there would be a way to update the Flux engine so that it uses the 3.0 native API, which is basically Flight SQL, and that the Flux engine could do the work itself to reorder the data in the way it expects it to be ordered. And maybe that would be performant enough. But for the time being, we're not focused on that. We're still focused on the core query engine, which means InfluxQL and SQL, and adding capabilities and performance to it that like right now it's already faster than 1.0 at a number of queries, but there's still some queries that's definitely not faster with. And we want to improve those situations and spend our time on that for now, and then see later what we can do with Flux. People in the community have expressed interest in actually self-organizing to do that work. So we've actually created a separate community fork of Flux that we're going to be pointing people to. And that fork will be a place where people can collaborate on this idea the thing is we can't do it in our primary branch because we run this in production in our cloud environment. It's just too difficult to try and like pull these changes in as people, like we need to give people the ability to like iterate on their own without having to go through our production pipeline. So that's the idea is in 3.0, InfluxQL and SQL are native and supported. Flux, we're still trying to figure out. I will say a separate thing about Flux, which is maybe not obvious to people, or for some people, maybe it is, but the language is highly polarizing, right? It's a new language, and a lot of people are like, I don't want to learn your stupid language. And I get that. I did not really get that 6 years ago, but I get it now. And so there's basically what we found is that a lot of people just didn't want to pick up the language. They wanted to work with something they already know. And again, with InfluxQL, it's a different language, but the thing is, it looks like SQL. It feels like an old friend, like you know it. So you can pick it up without having to do too many things. But with Flux, it was a serious adoption blocker for a lot of people. But then on the other side of this, there is a slice of people who took the time to learn Flux, and they absolutely love it because they can do things in that language that they could not do in SQL or in InfluxQL. And I think that is kind of a testament to the reason why we built the language, because we wanted something that enabled arbitrary processing inside the core of the database. So again, it's like one of those things where depending on who you are and how you look at it, Flux is either like a great thing and it's like, we need to keep pushing this forward, or it's why these guys build this language? This doesn't make any sense. It's tricky.
All right. Awesome. Thank you. Did you have a question, Laura?
No, just random commentary.
Yeah, we're running out of time very fast here, so let's finish up with something a bit different. Recently, HashiCorp announced their license change to the Bustle license, and you posted some thoughts on Twitter saying that it kind of gave you a bit of pause for thought on what source available in open source is or the future. And I'd love for you just to talk about that and maybe even bring it into the context of what's the future for the license on InfluxDB 3.
Yeah, so I basically, in my mind, open source, the Bustle, the community licenses, all those things, those are not open source. Those are basically the new version of shareware or commercial freemium software, right? It's commercial software, and frequently they will offer that software to you to use for free under certain conditions. And if you are one of the people who meet those conditions, maybe you're happy and you'll be able to use it, right? Tons of people continue to use MongoDB, the SSPL version. Tons of people use Elastic still after they changed their license, Redis, Confluent, literally every single infrastructure open source creator has changed their license over the last 6 years. Like there isn't one I can think of who hasn't, except for us, maybe. And I totally get the motivations to do that. But in my mind, like open source, I actually don't like copyleft licenses. I like AGPL, GPL. I don't consider them to be real open source. To me, open source is really about freedom to do what I want with that code. And if you put any sort of restriction on it, which a copyleft license does have restrictions on it, then that's, restricting my freedom. To me, open source is about freedom. So, and again, I think for a company that's producing open source code, you have to be okay with the fact that people are going to do anything with that code, including competing with you. And if you are not okay with that, you should not be putting that code out as open source, because that is what's going on, right? And generally, the best thing for a company to do that's building products and stuff like that is to only put open source code in something that they wish to have become a commodity, right? So the operating system, the server operating system that your servers run on, you want that to be a commodity. Many times you want the database to be a commodity. You want these core infrastructure components that are essentially not part of the value that you deliver to your customers. Essentially, you want them to be commodity so you don't have to pay a lot extra for those things, right? You want the price of those things to be driven down as low as possible. But if you are a vendor, the thing you sell, you don't want that to be a commodity. You want to be able to sell it for the highest possible price. And the problem that vendors have that create a project where their primary monetization path is essentially that project plus something or whatever, it becomes like, well, we're putting all this effort into the open source thing and a bunch of people are using it for free, and there are a bunch of freeloaders and there are a bunch of competitors who are taking our stuff, and then they decide to change the license. And the problem I have there are multiple pieces to this. One is, as the creator of a project, if I want it to get the broadest possible adoption, I want more people to use it, I'm incentivized to have that project be permissively licensed, right? All else being equal, a developer or a user looking at a piece of software, literally if everything else is the same, and the difference is a commercial license or a permissive Apache or MIT license, they're going to pick the permissive one, right? There's no reason not to, because you get a bunch of other stuff. So they choose that. But the problem now that I think the HashiCorp thing kind of highlights is it's just yet another vendor in a long list of vendors over the last 6 years who've changed their licenses. And now basically it's causing a lot of distrust in the developer community, because they see oh, here's a new open source project. And they look is that project by a VC-backed company, right? Or VC-backed startup. If it is, they're going to be like, well, it's an open source project, yeah, but I don't believe that it's going to continue to be open source, which is a totally valid thing to think given how things have been going over the last 6 years. So, previously, again, my thesis, if you want broadest possible adoption, put it in a permissive license. That idea is kind of getting damaged by the fact that people keep changing their license from permissive to something commercial, right? And I don't know if there's a solution to that. I do think separately, I think that HashiCorp probably made an error here. Like, the thing is, the license change only protects forward commits, right? You can't retroactively change a license. So they could have just as easily put all their development effort into a closed source private fork and then made the open source piece a downstream dependency of that closed source fork, and then not tell anybody about it, right? Just be like, yeah, we're just going to do this or whatever. Or conversely, they could have just said, we're going to donate this thing into a foundation, but all of our developers are going to be working on this closed source thing, right? The effect would have been the same in terms of the end outcome, right? Because you have this open Terraform fork, but the difference in everybody's perception of HashiCorp as a company would have been dramatically different, right? The business and commercial effect would have been exactly the same, which is all their R&D, all their development tokens are going only into the commercial software, which is fine. That is their right. If they want to do that, they should totally do that. And it's also fine if they want to change their license. That is totally permissible, right? Just because you create something open source one time doesn't mean you owe it to the world to continue for the rest of your life to put more and more into it, right? But I think there were more graceful ways to handle it that could have delivered the same business outcome for them at the very least.
All right, let's extend that question by one sentence and just say, like, does the fear that people have now, and rightly so, about single vendor VC-backed open source projects not always being open source, does that mean that InfluxDB 3 could be an Apache Foundation project in the future? Or are you not worried about the perception or the fear of people adopting it because it's a VC-backed single vendor project?
So I do not think we will put InfluxDB 3 into a foundation. My goal is to have a permissively licensed project. But the truth is, like, the problem with foundation projects is the bar is usually too high. Like, InfluxDB doesn't meet the bar for most foundations, right? There aren't multiple companies contributing to InfluxDB, version 1, 2, or 3, right? We're the ones developing it alone. So it doesn't really hit the level of a foundation. Terraform, you certainly could have put it into a foundation. I'm certain a number of foundations would have taken it gladly as a project, as a top level project. But InfluxDB doesn't hit that. It's not on the same level in terms of the contribution and like all this other stuff. There's that. I mean, I think I don't know, like, for the community and building trust with people and stuff like that, I don't know if there's a solution, right? I think the license itself matters, because if it's Apache 2 or MIT, then, people can do whatever they want with that software for all time, as long for that point. But maybe there's a model where you can commit to, transitioning into open governance over some period of time. I think early on in a project, open governance is actually more of a hindrance than, a benefit, because you want, like, a small, tight-knit group of people that are driving the project forward. But yeah, I don't know. It's tricky.
There are so many things I want to say and argue about here, but I know we're out of time. I think the one thing I guess I will say is the one little challenge, and I'll just kind of leave it here, I guess. Red Hat tried we're going to switch the order of things and make the downstream the open source part. And I would argue that the community really doesn't like that. So I don't know. There's a lot of different ways. I admit that I am a huge fan of the AGPL v3, but maybe that's why I will argue it. But we unfortunately don't have time, and I want to really badly.
To be continued.
To be continued. That's correct.
Yeah, we could have an entire session on open source licensing. I could talk about that for like hours.
Do this. This should be so much fun. Anyway.
All right. Yeah, well, we don't want to keep you any longer, so feel free to use 30 seconds if you wish, just to tell people where they can learn more about Influx, follow you on Twitter, anything like that. Feel free to shamelessly plug anything you wish.
On Twitter, I'm at Paul Dix. Influx, we're influxdata.com or influxdb.com. You can find us. 3.0 we have available as a multi-tenant cloud product, as a dedicated cloud product. And soon, open source builds or builds of 3.0 will be available, but we're not, again, we're focused on our commercial offerings at the moment for obvious reasons, but yeah.
All right. Thank you very much.
Thanks for joining us.
If you want to keep up with us, consider subscribing to the podcast on your favorite podcasting app, or even go to cloudnativecampus.fm.
And if you want us to talk with someone specific or cover a specific topic, reach out to us on any social media platform.
Until next time, when exploring the cloud native landscape, on 3.
On 3.
1, 2, 3. Don't forget your compass.
Don't forget your compass.